polygons, polygon angles, and the area of regular polygons. Okay, just 22 questions to open. Writing the name of each polygon. Septagon. Whoops. Or heptagon. Just like a 50-pence piece, although that would be a rulo heptagon. The sides have to be sort of pillared out and curved out such that the coin itself maintains a constant width. The way to sort of, if you're having trouble counting this, you can put a blob in one corner and then proceed clockwise, going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. And it's a decagon. The fact that you can sort of just visually see that these two sides are opposite here alerts you to the fact that it will be an even-sided polygon, whereas over here, because you get a line there and a dot there, that will be an odd number of sides. Like here, for example, I can just see that it has an odd number of sides immediately, and I know that it's a nonagon. And a hexagon, which is the bestagon. And now they become irregular. So this is an irregular hexagon. Oh, do we have to say the name? Say that they're all regular when they're regular? I believe so. That's interesting. Okay, that's regular. That's a regular nonagon. That's a regular hexagon. And here, this is an irregular hexagon, as the sides and angles don't all match. So for here, now you would actually have to use my technique. So 1, 2, 3, 4, 5, 6, 7, 8, 9, like that. But watch out, by doing that, aren't you saying that these sides are all like the same in length? Yeah, you run that risk. So you may just wish to go using your pen or pencil without touching the page. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And once you reach the dot, stop. So it's an irregular nonagon. One, 2, 3, 4, 5, 6. Irregular hexagon. One, 2, 3, 4, 5, 6, 7, 8, 9. Irregular nonagon. State if each polygon is concave or convex. So this is a concave polygon, as all the interior angle, as no interior angle exceeds 180 degrees. Likewise here, whereas this one is convex. Oh my goodness me, I got those mixed up. Not concentrating enough. Okay, convex, convex, and that one's convex. Okay, this is a concave polygon, and here is the concavity, right? It's like the word cave, you know? And there's the reflex angle exceeding 180 degrees. And there's another one over there. Okay, so convex, concave, concave. This particular concave polygon would be called a dot. A concave quadrilateral is called a dot. Now state if each is regular or not. So I'm going to do a tick for regular and a cross for not. So that's regular, irregular, regular, irregular, irregular, and regular. And the way that you would actually establish and verify that is using a ruler and a protractor. But here I'm just going sort of by eye. So construct a concave hexagon. Okay, well, the thing is about that is, like, how can you do it systematically? You could sort of think that it always has to have that. As long as you have that, you have a concavity. And that takes up 4 sides already, so then there you go. Which are impossible? A regular convex octagon, is that impossible? No. That's fine. A concave trapezoid, is that impossible? That's impossible, yes. A convex irregular 20gon, that's perfectly fine. A concave triangle, that's impossible. A concave equilateral pentagon, well, you know, you can sort of imagine drawing the first 3 sides of a pentagon, an equilateral pentagon, and then ask yourself what happens if instead of doing this business, whether like that, what happens instead if I do this? Should be fine, right? And it is. So that's actually possible. But let's see the verdict. Yeah, that's all valid and fine. And now polygons and angles. And there's 32 questions to contend with here. Find the measure of one interior angle in each polygon. Round your answer to the nearest tenth if necessary. So going by eye, this is a regular pentagon, so that means it has an interior angle of 180 degrees. For an octagon, by memory, it's 135 degrees, but I might be wrong. So just use the formula of n minus 2 and then multiply that by 180 and then divide that by n. So this would be 6 times 180, which is 1080. And divide that by 8. Divide 1080 by 8. That is indeed 135 degrees. So 1, 2, 3, 4, 5. This is an 11gon. By the formula, n times 9 times 180 rather, that gives us 1620, and then divide that by 11. 1620 divided by 11, well, that would be Beg your pardon, 1520, is it? No, 9 times 180. Okay, then 1620. No, come on, 9 times 180. Yeah, 1620, and then divide that by 11. Okay, so that would be 147, and then there's like a remainder of 3 there, right? 147 and 3 11s. I would say so. And so check. Yes, but they want it to the nearest 10th. All right. So I know that dividing by 11 gives you 0.090909 forever and ever. No, it doesn't. It actually gives you that. And make this approximate. Regular hexagon. Know this by heart. This is now a nonagon. So 7 times 180 to give you 1260, and divide that by 9 to give you 140. This will have an even number of sides because of, and just there like that. But you check, and then you double, so you get a 12gon. So this is a dodecagon. So you do 10 times 180, which is 1800, and divide that by 12 to get 15 with a 0 on the end. So 150 degrees. And we check, and that's correct. Now for a regular 24gon, it would be 22 times 180, which is 3,960. And then you have to divide that by 22. Wait, is that correct? 22 times 180. Yes, that's correct. 3,960. And then divide that by 24. 3,960 divided by 24. $165. For a regular quadrilateral, just 90 degrees because that is a square. For a regular 23gon, 21 times 180, which is 3,780, and then divide that by 23. 164. I'm gonna guess 164. I didn't. No, that's not right. Don't guess. 21 times 180. And divide by 23. So we have 1 there. 1 4 there. 6 there. 1 0 there. 4 there. And the remainder is 8. So it becomes 8 over 23. And 8 over 23 is approximately a third. So roughly speaking, it'll be 164.3 degrees. For a regular 16 gon, 16 minus 2 is 14, and 14 times 18. 14 times 18, 252, but I don't know if that's right. Anyway, 252 divided by 16, it's about 16 because 16 squared is 256. But this is not right. It's 2,520 divided by 16. So 2,520 divided by 16. $157.5. That's correct. Find the measure of one exterior angle in each polygon. Round your answer to the nearest tenth if necessary. So this is a regular decagon, and therefore we just need to divide 360 by 10, and so we get 36 degrees. This is a regular septagon or heptagon, and so we need to divide 360 by 7, and so we get 51. 51 point 42857. 51.4 degrees. This is a regular octagon, and so divide 360 by 8 to get 45 degrees. This is a regular pentagon, so divide 360 by 5 to get 72 degrees. And we check. And it's correct, and that's good. This is a regular 11agon. So divide 360 by 11 to get 32 and 8 over 11. 32 and 8 over 11, so 32.72. So 32.7 to the nearest tenth. This is a regular 9gon, so 360 degrees divided by 9 is 40 degrees. And now for these other 4 here. but checking those. That's correct. 360 divided by 13. 24 and 8/13. 24 and 8/13, so around 24.7. But we can actually verify this by doing 80 divided by 13 and continuing on like that. So that would actually be closer to, it would be closer to 6. That's closer to the truth. Regular 16 gone, 360 divided by 16, so 180 divided by 8, so 90 divided by 4. So we obtained 22.5. Regular 20 gone. Regular 23 gone. 360 divided by 23. Okay, so that's 100 and 360 divided by 23. That's 100 and, no, it's not. 360 divided by 3 is 15. Uh, 15 point. Uh, 6. And check. Closer would be 7 in both of these cases, actually. That's alarming. All right. Find the interior angle sum for each polygon. So we need to just do n minus 2 times that by 180 in all cases. So for the septagon, so that'd be 5 times 180, which is 900 degrees. For this here, which is a decagon, that would be 8 times 180, which is 1440. 3 times 180. 6 times 180. And check. And that's correct. And nine times 180. Seven times 180. Here and here 16 times 180. It's that, isn't it? 10 times 180. 13 times 180. And check. And that's correct. What is the exterior angle sum of a 500 gon? Just 360 degrees. Is there a regular polygon with an interior angle sum of 9,000 degrees? And if so, what actually is it? So we have to do n minus 2 and then times that by 180 to get 9,000. And so divide 9,000 by 180, which is the same as 900 divided by 100, which is the same as 900 divided by 18, which is the same as 100 divided by 2, so 50, and then add on 2, so 52 gon is the name. And that's good. That's all solved. And next up, looking at areas of regular polygons. And there are 18 such problems. Find the area of each regular polygon. So, well, the height will be 8 root 3 over 3. And so you can do base times height. So you get 64 root 3 over 3. And then divide that by 2. So you get 64 root 3 over 6. Or 32 root 3 over 3. Now, up until this point, I have not learned the formula for a regular n-gon, the area of a regular n-gon. And so it is incumbent upon me to actually learn that formula. So how am I going to do this? I'm going to do something like this. I am going to try to figure it out for myself. How about that? Yes, that's what I will do. I will figure it out for myself. Okay, so area of n-gon with side of length A. So because, well, I don't want to use like the transcendental functions. No, well, let's say that you're given the what's the, I need to know these terms. Distance from the center of a polygon to its vertex. Name for distance from center of septagon to midpoint of edge. Okay, so the official technical name is radius and apothem. But let's get the pronunciation right. See, this is another thing. I want to actually speak mathematics. And so I'm not just going to them, apparently. Okay, so there's a disagreement there. Circumradius, huh? Better get my terms straight. And better get the pronunciation correctly. Apothem. Apothem. Apothem, apothem, apothem. All right, so they call it circumradius. Circumradius. Why not just simply radius? Gemini calls it the radius. All right, so I'll comply with the terminology of the field. So say if we are given the... No, there's an important question now. What is the diameter? These are all regulars, by the way. Okay, so anyhow, area of a regular n-gon with a side of length a. Okay. Divide that by 2, of course. And then times all of that by n. Right? Okay. Above them. So it's n times a times l. So in this one, wrong. It'd be like that instead. And then do the work and figure it out. And trying. Ooh, nearly. Very close. Very close. Okay. But this one I genuinely don't get. Why did I get that wrong? The height would indeed be 8 root 3 over 3. and times that by 8. 64 root 3 over 3. And divide that by 2. 64 root 3 over 6. So why are they saying that? Why am I not getting this? Oh my goodness me. Oh man. How could I have forgotten? The centroid of a triangle partitions it into 2/3 and 1/3. Goodness me. Okay, fine. So the whole thing is 4 root 3, fine. Times that by the height. 32 root 3. Divide that by 2. 16 root 3. Better. Much better. Okay. So this is an 8gon. So it'd be 14 apothem times side length times the number of sides, but divided all by 2. So it'd actually be like that. So it'd actually be like that, and then do the actual work involved. There. The apothem times the side length times the number of sides, all divided by 2. The apothem times the side length times the number of sides, all divided by 2. So 5.1 times 7.5 times the number of sides, 5, and then all of that divided by 2. Okay, so $382.5 divided by 4. $95.625. It seems. Okay, correct. Good. The apothem times the side length times the number of sides divided by 2. How many sides are there? And then divide all that by 2. So it's the same as 16.5 times, that's 6, and that's 9, so 54. But you can do better. Double that and halve that. So 891. The apothem times the side length times the number of sides, and then all of that divided by 2. So that's 30 times that. So that's 150 root 3. And there you go. So now we've got a pentagon with an apothem of 7.3 and a side length of 10.6. And so we do 5 times 7.3 times 10.6 and divide everything by 2. NaL over 2. NaL over 2. Number of sides, side length, and the apothem. You want to get it in the right order. I know it's immaterial, but it will help cement the formula better. See? So that's 53, and 53 times 7.3. $386.9. $193.45. Oh, so it would seem, okay, a triangle with an apothem of 14 and a side length of 28 root 3. So remember, number of sides times the apothem times the side length, and divide all of that by 2. So that's really 21 times 28 root 3. And 21 times 28 is 588. So it's 588 root 3. Hooray! I did it. Okay. It's a 7-gon, or septagon, or heptagon, with an apothem of 21.8 and a side length of 21. So 7 times 21.8 times 21, and then all of that divided by 2. So 10.9. $1602.3. An octagon with an apothem of 14.1 and a side length of 11.7, and all of that divided by 2. So 4 times that. And now doing that calculation. $164.97. 164.97. Oh, okay. So do 165 and quadruple it and take away 0.12. So that'll be 660. So 659.88. Good. Use what you know about special right triangles to find the area of each regular polygon. Leave your answer in simplest form. Okay, so What I know about special right triangles here. Or you could just simply use the formula here. I mean, base times height divided by 2. What is known about special right triangles? Okay, so we're actually out of time here, so I have to come back to this. Be well.